Hello and welcome everyone to week 4 of interactive live sessions for the course on fundamentals of convective heat transfer. The course is being offered by NPTEL and instructed by Professor Amaresh Dalal from IIT Guwahati. Uh, I'm a PhD scholar at IIT Madras. My name is Debjit, and together we will be solving tutorial problems and discussing the course material along the way. So without further ado, let's begin today's session with question number 1. Question number 1 says that in integral formulation, the conservation laws are satisfied in an average sense. Average sense. So this statement is given. You have to select whether it is true or is it false. So when it comes to analysis of laminar boundary layers, we have seen that there is exact analysis, which is done by simplifying the Navier-Stokes equation and then trying to solve it using similarity method. Blazier's solution is one such solution for finding out the velocity, and Polhausen solution is a similar method used to find out the temperature field, used to resolve the temperature profile within the boundary layers. So that is the differential analysis. Other than that, or the exact analysis, other than that, there is an integral analysis in which the laws of uh, motion or heat transfer, they are solved for an integral control volume, and it's not as accurate as the exact solution, but however it gives some reasonable results with some other advantages such as simplicity of use and so on. So that is what integral formulation is. Now okay, so the answer is integral formulation is indeed, in integral formulation, the conservation laws are satisfied in an average sense. So we lose the idea of variation along y, and we get an average sense. So what is exactly the difference between integral and differential analysis? So let's say this is the boundary layer forming over a flat plate. Now in exact solution, the control volume is this. So and this is infinitesimally small. This is say delta y and delta x, and both delta x and delta y tending towards 0. So in this case, if we resolve this, we get the distribution over our entire ranges of x and y. But on the other hand, in integral solution, what is done is the case is similar. So in this case, uh, this is our control volume. In this case, our uh, the delta x, this still tends to 0 and this still is infinitesimally small, but the y the y coordinate of this control volume ranges from 0 to delta, whatever is the hydrodynamic boundary layer thickness. So that's why we, after solving this, we lose the sense of variation along y and we only get the variation along x. So in that sense, the conservation laws are satisfied in an average sense. So we get an average over y, not particular values over different points in y. Hope that makes sense. Okay.
Yes, yes, sir.
Okay. So moving on to question number 2. What are the advantages of integral formulation of laminar boundary layers? Is it option A, simpler than exact solution? Is it option B, reasonably low errors? Option C, more flexible than exact solutions? Or is it D, all of these?
Simpler than exact solutions.
Okay, so that is true. The other two options are also true. So the correct answer would be all of this. So simpler than exact solution because the entire formulation becomes simple. The errors that we will see if we look at the lectures in different points, our course instructor, Professor Dalal, he stops and points out what is the error percentage from the exact solution, and we see in those consecutive steps that even a much simpler method, the integral formulation, that gives reasonably low errors when compared with the exact solutions as well. So that's what makes this integral formulation very powerful. So errors are also reasonably low, and moreover, these integral solutions are much more flexible than exact solutions because it allows us to assume any velocity profile that we want. It may not be the actual case, but however, it gives a very good, very accurate approximation of the exact case. Okay, so that is why all these are correct. And all these are actual advantages of integral formulation. That is why the correct answer would be all of these.
Okay.
Okay.
Okay, sir.
So moving on to question 3, this is a numerical type question. So assuming a linear velocity profile, so here we assume that the velocity profile within the boundary layer is linear. So what we are assuming that if there is a flat plate and there is a boundary layer forming, so the velocity profile within this is a linear one, where this is u infinity and this is u at any point is linearly varying with it. So u by u infinity is equal to y by delta. And using this approximate momentum integral method, find out the expression for Cf by root under Rex. Okay, there is a small mistake here. Let me try to correct this. This root over is entirely over Rex. And a hint is given that for linear velocity profile, delta by x can be approximated as 3.464 over under root Rex. So let's try to solve this one. Will you take time and try to do this?
No, sir, no.
Okay. So
Yes,
I'll
please.
directly. Okay, this is
Yes.
an easy one. You could have attempted even without going through the recent lectures. But anyway, so we will look at it. So here in the final answer there is CF. So what does CF constitute of? CF is equal to tau wall divided by half rho u infinity square. This is fine.
Yes, yes.
Now this tau w has to be found out. Okay, so let's keep it at here and we will write the expression for tau w. What is it? How can we write this? This is the shear stress at the wall.
Is this 0.332?
No, no, not that. Just the actual formula of tau w. How is it calculated in any case? Not just boundary layers of any specific kind. It's what mu into dou u by dou y at y equal to 0. This is simple Newton's law of viscosity.
Yes, yes, yes,
Okay.
yes.
So now in our case, u can be written as u infinity into y by delta. Is that correct? That's what is
Yes.
given.
Hmm.
So now if we differentiate this, so dou u dou y, this becomes u infinity by delta. Simple. This is for all values of y, even at y equal to 0. So we will plug in this value over here. So our tau w, this becomes mu into u infinity by delta. Now we will go back here. So now we will write that Cf is equal to mu into u infinity divided by delta. And in the bottom we have half into, okay, so this 2 of half we are bringing it in the numerator. So it's like this. Okay, and 1 u infinity we will cancel. So it boils down to 2 mu by rho u infinity into delta. Okay,
Yes.
okay. So now for linear velocity profile, if we perform this approximate momentum integral method, we will land over here. We are not, that derivation is not required over here, but this is given in the hint only. So if we use this, so here delta can be written as 3.464, whatever value, into delta divided by Rex. We will, sorry, not delta, into x, and we will plug in this over here. So here Cf becomes 2 into mu divided by rho u infinity. Now this value of delta. So 3.464 x and divided by under root Rex. So we will move it in the numerator. So that is an Rex we will write as u infinity x by nu. And over here this mu by rho part, this is equal to nu, right?
Hmm.
So, and okay, so this is new. There is a nu under square root over here. There is a u infinity here and a u infinity under square root here. There is a x and there is a x with square root here. So if we cancel those out, this simply becomes 2 by point 2 by 3.464 into
Mu
under root.
upon root.
So we have one u infinity in the denominator, one x in the denominator, and one nu in the numerator. And this is nothing but Reynolds number to the power 1 by Reynolds number at x. So, and this is all equal to Cf. Now, if we simply move this, okay, let me write it down more clearly. So this becomes, okay, can you perform this division for me? What is 2 by 3.464?
0.5773.
Thank you. So 0.5773. Leaving out the 3, let's keep it to 0.77. And this under root 1 by Rex, this is like this. So it comes in the denominator. So wait a second, did I make any mistake? Delta by x is this, delta equal to x and that. Delta, I'm putting here.
Sir, is it necessary to put the value of u infinity x upon nu as Rex? Because
Yeah, otherwise it won't be simplified, no?
we want the value of Cf upon Rex only. We can directly do it, na?
Okay, let's try doing that. Let's see. I will remove all this.
Now what I have done, delta by x is that expression, okay?
Yeah.
So directly we will get the value of root
Okay,
of Rex.
let's keep Rex. Okay.
So root of Rex as 3.464
Hmm.
x by delta.
Okay. So CF, this would be 2. Okay, I'm writing this mu by rho as nu over here. So nu, there is a u infinity here, and we are writing the value of delta over here. So this becomes under root Rex divided by 3.464 into x. And this thing, this is nothing but Rex, right? U infinity x by mu. So this boils down to that 0.577. There is a under root Rex in the numerator, and in the denominator there comes another Rex. So this becomes Cf is equal to 0.577 into under root Rex. Okay, so I think the question over here I have given wrong. So essentially this would boil down to Cf into under root Rex equal to 0.577, which is a numerical value, and this would be the answer. So let me correct the question. It won't be this, but rather find the expression for Cf into under root Rex. Okay, I'm sorry for the mistake.
Just 1 minute, sir.
Okay.
Actually, CF into RAX multiplication करना है. Okay. Just minute, sir.
Yeah, sure. Take your time and let me know if there is any issue. Sure.
X.
Moving this to up, get down, and writing into u infinity by delta. Delta is going in the denominator. Rho u infinity square. U infinity gets cancelled out. This becomes mu. There's u infinity in the bottom. Delta can be like this.
Yes, sir.
It's safe
Got
like
it.
this. Okay. Okay.
It's finished.
Let's move on to the next question. Question number 4. So question number 4 says that for laminar boundary layer flow over a flat plate with air at 20 degrees Celsius and 1 atmospheric pressure, and for that condition the Prandtl number is given. Prandtl number equal to 0.709. The thermal boundary layer thickness delta T is approximately 21% larger than the velocity boundary layer thickness delta. Determine the ratio delta by delta T if the fluid is ethylene alcohol, a different fluid whose Prandtl number is also given, but under the same flow conditions. So how can we do this? So let's see. Uh, for the first case, that is for the first case, that is air, we know that delta over delta T is equal to Prandtl number to the power m for any flow condition in general. We do not know the exact flow condition, but the form is similar to this. Now,
Yes.
uh, what is given here? The value of Prandtl number is given, and it is said that the thermal boundary layer delta T is 21% larger than the velocity boundary layer boundary layer thickness delta. So what we can do here is that we can write we can take delta to be 1, and we know that delta T is 21% larger. So
1.21.
1.21 we can take, and Prandtl number, this value is also given, so that is nothing but 0.709 to the power m for whatever flow condition. We do not know the flow condition, but we can find out this value of m from the other given data. So if we take log on both sides, so m can be written as log of 0.709. Sorry.
M is 0.5542.
Okay, let's see. 1.21 divided by log of 0.709. This is what you calculated, right? How much was it?
0.5542.
0.5542. Let's keep it to 0.55. So we got the value of m for the flow condition that is being considered here. Now it is said that for a different fluid under the same flow conditions, what will be the ratio of delta by delta T? So for ethylene glycol, I'm not writing this entire thing. I'm just writing it like this: ethylene glycol. So here, delta by delta T, this would also be Prandtl number to the power m since the flow conditions are the same. Now
M is going to be same now, na?
m is going to be same. So it's nothing but 211 to the power 0.55. Can you please calculate and find out how much is this?
It's 19.41.
19.4. Yeah, it should be around 20 something. 1920. So 19.4, is it?
Hmm.
Yeah. So this would be the ratio of delta over delta T for ethylene alcohol. Oh, sorry, I wrote ethylene glycol over here. Let's say ethylene alcohol. Ethylene alcohol is nothing but ethanol. So we can write ethanol, and the value of the ratio delta by delta T would be around 19.4. Okay, is it clear?
Yes. Yes. Yes.
Simple questions. We will move on to question number 5. A lot of data is given, but this question is very easy, I promise. So let's have a look at it. So air at a temperature of T infinity flows over a flat plate with a free stream velocity of U infinity. The plate is maintained at a constant temperature TW. Let's keep drawing this as we read this question. So there is a flat plate, there is a free stream with velocity u infinity and temperature T infinity. There is a boundary layer forming, both kinds, delta as well as delta T. Let me draw this with a different color. So there is a hydrodynamic boundary layer forming as well as a thermal boundary layer forming. And the plate is maintained at a constant temperature TW, that is the temperature of the plate. Now, the velocity and temperature of air at any location are given by this. So the profiles of velocity and temperature are also given. U by U infinity is equal to sine of pi y by 2 delta. So instead of a polynomial or any other kind of profile, it follows a sinusoidal profile. We can assume this with, you know, a significant amount of reasonability. And similarly, the temperature profile is also given. This follows a polynomial variation of the second order, since y by delta t cube square is the highest order term over here. Now, where y is the distance measured from the plate along its normal, and delta and delta t are hydrodynamic and thermal boundary layer thickness. These are all, common notations which we have been using from the start of the course. The question is, find the shear stress at the plate surface. The question is, find the shear stress at the plate surface. So nothing but this tau w we have to find out. There are a ton of other information also given. The u infinity, value of u infinity, delta y delta t, the flow condition, that is Prandtl number to the power one third. The tw value is given, t infinity is given, the properties of the fluids are also given, mu, cp, k, as well as the thermal boundary, the hydrodynamic boundary layer thickness is also given at a particular x.
Hello, sir.
Yes. Could you
No, no,
make
no.
an attempt?
No.
Okay, so let's have a look at the correct answer is pi by 200. We will see how to land there. So basically, as I said, we have to find the shear stress at the plate surface. So this is what? This is mu into rho,
Du by dy.
rho y at y equal to 0. Our value of u is given here. So u can be written as u by, sorry,
Du infinity
yeah,
sine pi
u
y.
infinity sine of pi
Pi
y
y by 2 delta.
by 2 delta. So this
2
is given.
delta
So if we differentiate this, dou u by dou y, this
du
becomes
infinity.
u infinity. This all this stuff comes out pi by 2 delta, and we get cos of pi y by 2 delta.
Twice delta.
Correct?
Yes.
And at y equal to 0, what happens at y equal to 0? This
1.
argument becomes 0, so cos
So
of
u
this
infinity
becomes 1.
pi by twice delta.
Correct. So this becomes u infinity pi by twice delta. We will simply plug in this value here, and that would boil down to tau omega being mu into u infinity pi by twice delta. Now,
Yes.
the value of delta is given, the value of mu is given, the value of u infinity is also given. So we will simply plug in all those values, and also value of mu is given. Okay, we will simply plug in all those values. Mu is 2.5 into 10 to the power minus 5 into u infinity is 10. We will keep pi as it is, since there is a pi within the options as well. So this is 2, and delta is 0.025. Sorry, 0.025. So this is nothing but 2.5 to the power minus 2, right? Yeah. So we can cancel these out. So that would essentially be 10 to the power minus 5 by 10 to the power minus 2. So that would be 10 to the power minus 3 over here. There is a 10 here and a 2 at bottom. So this becomes 10 to the power minus 2. If we multiply these two, it becomes 10 to the power minus 2. And if we simply bring it down to the numerator, it becomes by 100. And there is a 2 here. So this would boil down to pi by 200, which is the correct answer. Option C.
Yes.
Is that
Point
clear?
not 1570. I solved by this way. Okay. In terms of pi, we require pi by 200. Yes.
Correct.
Yes.
So,
Yes.
okay.
So, what is the use of that temperature profile then?
Temperature profile. If a different question would have been asked, that find out, let's say, the heat transfer coefficient H equal to what? Let's try. Let's add this as a question.
Okay.
So how
Okay.
can we find out H?
H.
What is H? We'll, uh,
Minus k t by.
have you noted these things down? Then I will. Okay, let's
Yes. Yes. This is over. This is over.
okay. Let's keep this. Give me a
Mhm.
second. I will add another page afterwards and do some working over there. Okay. Okay. Uh, okay. I hope this slide is visible. Yeah.
Yes.
If we have to find out H, how can we do that? Can H is written as K into dou T by dou Y uh, by A, right? Sorry, Q equal to H A into delta T, and this is equal to K into dou T dou Y. So we can write. Okay, no, we can cancel out this A and simply take it as Q dot double prime. So H delta T equal to this. So H can be written as K dou T dou Y divided by delta T, or T minus T infinity. Correct?
Yes.
Okay. So since the profile of temperature is given, from here we can figure out dou T dou Y and then plug in the other values. So if we simply take this, uh, okay, so T can be written as, let me write it over here. So T can be written as uh, TW plus T infinity minus TW into 2y by delta T minus y by delta T whole square. Correct. And if we take a differential of this, dou T by dou Y, uh, all this one goes to 0 since this is a constant with respect to Y. This stays, and inside this we get 2y delta T, and here we get 2y by delta T square, and at uh, y equal to 0, this becomes nothing but T infinity by minus TW. This term goes to 0 since we're putting y equal to 0, so this becomes 2y delta T into this. We will use this dou t by dou y equal to dou t by dou y at y equal to 0 equal to 2 by delta t into t infinity minus tw over here. So here we will put h equal to k into this thing, 2 by dou t into tw minus t infinity, and here also in the denominator we have a tw minus t infinity. These two things get cancelled, and h simply becomes 2k by delta t. And going back, we know that delta t delta by delta t is equal to Prandtl number to the power one third. Value of Prandtl number is not explicitly given, but the material properties are all given, and delta is also given. So we can figure out delta T from there, and after that we can figure out H. So if we try to do that, uh, so Prandtl number is mu by alpha. Mu is nothing but this nu is nothing but mu by rho, and alpha can be written as rho Cp uh, k by
K
rho.
by rho C.
So
Hmm.
alpha can be
Yes.
written as k by
Mu,
rho Cp. So
so it is mu Cp by K.
mu Cp by k. And what if we put in all these values? Mu is 2.5 into 10 to the power minus 5. Cp is 1000 if I am not wrong. Yeah, Cp is 1000, and
Point
is
not
how
four.
much? Point not 4. And if we try to do this, where will we land up? So this would become 10 to the power minus 2. 10 to the power minus 2 if I take it down. So this becomes what?
Point six
4.
two five.
And 2.5 by 4 is
6
0.625.
to 5.
This is our Prandtl number. And we know delta over delta t is equal to Prandtl number to the power one third. So that is, sorry. So that is 0.625 to the power one third. How much is this?
Which one, sir?
Okay, are
Just,
my annotations not coming on? Sorry.
no, no. Oh, not coming.
They were coming earlier and then paused simply. Let's see. Okay. So it had paused up until here, that divided by 0.04. We had figured Prandtl number out to be 0.625, and delta by delta t is Prandtl number to the power one third. Prandtl number we know 0.625 to the power one third. Can you help me figure this out? What is the value of this?
0.8549.
0.8549. I'm taking it as 855. And From here, the value of delta is known. Delta T has to be calculated. So delta T becomes delta by 0.855. Delta is nothing but 0.025. 0.025 divided by 0.855. So it would be just a bit less than 25 millimeters. How much is it?
That's right. 0.20.
A bit more than 25 centimeters. Sorry.
0.029 meter.
Not
29.
29, 29. So that is around 29 millimeters. This is our delta T. Now we get back to H. 2 into value of K is given. K was what? 0.04. 0.04. And delta T is 0.029. So how much would be H in this case? 0.08 by 0.029.
It's 2.7586.
Point
2.7586.
0.27
No, 2.75.
or 2.75. Okay, yeah, there is a point zero here. So 2.7 something.
5.
Yeah, this is watt per meter square Kelvin.
Kelvin.
This is how we can find out the shear stress as well as the heat transfer.
Convective heat transfer coefficient.
Okay,
Yes. Yeah.
moving on. So we'll move on to question number 6. The Leibniz integral rule gives us a formula for differentiation of a definite integral whose limits are functions of differential variables. Is this statement true or is it false? In deriving of the approximate momentum integral analysis as well as the energy integral analysis, we have to use Leibniz integral rule. So does that rule give us a formula for differentiation of a definite integral whose limits are functions of differential variables? Is this statement true or is it false?
True.
True. Correct. So the expression shown below is the Leibniz formula. So what usually come across is within our momentum integral formulation, this is a term that shows up. This is a term similar to this shows up where ax is usually 0 and bx is either delta or delta t. And remember, both of these are functions of x. And in here, f could be u, could be anything else also. So that is also a function of x as well as y. Sorry, x as well as another independent variable y. Here the second independent variable is t, but it could be y. And what we want from it is we want to reach to this left hand side where we can take the uh, differentiation out of the integration. But in order to do that, we need to make sure that these terms are taken care of. So its integral rule allows us to do that. Okay.
Yes.
Moving on, we'll move on to question number 7 of today's session. This is once again a numerical. So a flat plate has a thickness of 5 centimeter, thermal conductivity 1 watt per meter Kelvin. The convective heat transfer coefficients on its two flat faces are 10 watt per meter square Kelvin and 20 watt per meter square Kelvin. So what I'm essentially saying is that there is a plate like this and there is this one face, let's say we will call it face 1 and another face 2. It has a thickness of 5 centimeters, and on these two walls, in this wall there is a heat transfer. So there is a H1. This H1 is equal to 10 watt per meter square Kelvin. I'm not writing the units down over here. And there is this second wall. This has an H2 of 20 watt per meter square Kelvin. So the question is, what is the overall heat transfer coefficient? Sorry. what is the overall heat transfer coefficient in watt per meter square Kelvin for such a flat plate. So this is very simple. There are three ways in which heat flow is being resisted. So we can use electrical circuit
And
analogy and try to figure out the overall heat transfer coefficient.
just minutes.
Yeah, take your time. Let's do this. So there is, let's say, there is a temperature T1 over here, and there is a temperature T2 over here, and heat is trying to flow in this way. Q is trying to flow from the left side to the right hand side. And yeah, there is a thermal conductivity of this is also given, which is equal to 1. Area can be taken as unity, so it's per unit area heat transfer. So this Q is nothing but Q dot double prime, the rate of heat transfer per unit area.
Answer is 5.
Answer is 5. Let's look at the solution. Correct. Answer is 5. So how can we do this? So overall heat transfer coefficient U is okay. Let's not. This is equal to 1 by the equivalent resistance Re. And how can we find Re? We can take all those in series. So taking all those individual resistances in series, we can find out that it's 1 by H1 plus L by K plus 1 by H2, and putting in all these values, so it's 1 by 10 plus L is 5 centimeters, so 0.05 divided by 1 plus 1 by 20. How much does this become? This is zero point 0.1 plus 0.05 and
Plus 0.05.
0.05. So this is zero point 0.1, this is zero point 0.2.
Point 2.
Correct?
Point 2. Hmm.
So this is the equivalent resistance, and if we simply take the reciprocal of that, it's nothing but 5. Hence 5 is the
Yeah.
answer. Okay, simple.
Yes.
Moving on to question number 8. So for laminar boundary layer flow over a flat plate with uniform heat flux condition at wall. So if this is the condition, we are saying that instead of a uniform temperature, we are saying that the heat flux from here, from the wall, that is Q dot double prime at wall, this is some constant, uniform heat flux. Then the temperature at wall is given as, so now this temperature at wall, this is no longer a constant, but rather becomes a function of x. So this uh, T wall of x equal to T infinity plus c, some constant c, into x to the power m, some parameter m. So we have to select what is the correct value of m. Is it half? Is it minus half? Is it 1 or is it 0?
Okay. X. No idea.
Okay, so if you look at the answer, it is half. So this is what basically happens. This can be found out two ways. If we assume uniform heat flux condition, then by solving it, ultimately this, sorry, why did I write T? So ultimately T wall of x, this comes of the form T infinity plus C into under root x. This is one way we land over here. Other way, if we assume that the heat flux condition, sorry, if we assume that the temperature condition at the wall, T wall is similar to this, some T infinity plus C into under root X, then also we find out that the heat flux Q wall, that becomes a constant in that case. So conversely, these uh, situations can be found out. So this is what under root x means, simply x to the power half. That is why the correct value of m over here would be equal to half.
This
Uh,
one is the derived equation or
yeah,
the
this is
constant.
derived in the lectures. Please go through them, and if you
Yes.
have any
Uh,
doubts, please do ask.
yes.
So moving on, move on to question number 9. So which of the following assumptions are correct for laminar boundary layer flow over flat plate with uniform heat flux condition at wall? So this is also a similar case, that there is a uniform heat flux at the wall. Q dot double prime is equal to some constant, and there is a boundary layer forming. So in this case, uh, what are the assumptions taken? Is there negligible viscous heat dissipation? Is there no internal heat generation? Or is the flow taken as incompressible flow? There are four assumptions given here. So pick out the correct ones, and once you figure out the correct ones, select the correct combination from the options given here. So is it A 1 and 2, B 2 and 3, C 1 and 3, or is it D all of them 1, 2 and 3?
2 and 3.
Let's look at the correct solution. No, it's D, all of them. So in we will go through each assumption one by one. Negligible viscous heat dissipation. That viscous heat dissipation term, capital phi, that is ignored in all low Mach number flows. So that is the same for uniform heat flux condition laminar boundary layer flow as well. So that's why one is correct. No internal heat generation within the flow. There is no heat generation. There may be any heat generation within the wall, due to which there is this uniform heat flux coming into the flow, but within the flow there is no q dot that is equal to 0. So that is why no internal heat generation is also correct, and the flow as usual is considered to be incompressible flow. So the temperature differences are not large enough to create density differences resulting in compressible flow. This is something which we will see in natural convection. In free convection, the momentum is the driving force. In natural convection, there we will see that due to temperature difference, there will be density difference which will drive the flow. So in that case, incompressible flow assumption won't be correct. But in this case, we are still in the forced convection regime. Here, incompressible flow is one of our assumptions. So option 3 is also correct. So as a result, 1, 2, 3, all of the above would be the correct solution.
Sir, can you discuss number one again? Actually, I'm not
Number
getting.
one, the viscous heat dissipation term. This capital phi, which shows up in the energy equation. So
Mm.
how do we write energy equation? Q dot E dot x plus V dot E dot y equal to, there was this dp dt term plus
Material derivative.
material derivative plus this temperature diffusion term
Mm.
plus there was this viscous dissipation term. There was some factor in front of it. I don't properly recall. I'm sorry for that. But
Mm.
what happens is this is the heat generated due to viscosity. If there are, say,
Yes, yes, got it, got it.
there are
This.
large, velocity gradients that creates a, there is a large velocity gradient, and there has to be a large, mu as well, or the coefficient of viscosity. If both of them are large, that viscous dissipation creates some heat. So it's similar to rubbing our hands. If we rub our
Yes,
hands,
yes,
there is a
it's
friction and heat is
it's
getting
in
created.
friction between layers.
Correct. So that also
Mm.
creates some heat, and that is considered in some cases, but in these cases where the Mach number is low, where the velocities are low as well as viscosities are low, there we don't have to worry about this term, and this is neglected in most cases.
Yeah.
That is why negligible heat dissipation. Can you think of any engineering application where this might become important? Viscous heat dissipation.
Viscosity. It is actually application. Highly viscous flow, like uh,
Not only that, velocity gradients has to be high as well. So one very classic examples where this becomes important is in journal bearings. So this is a
okay.
bearing, a steel shaft or something. This is the bearing. Draw this correct. So this is the bearing. It's lying on some support, and this is the shaft which is rotating. This
Hmm.
rotates with say some omega, and there is this lubricating fluid in between. This shaft lies within that fluid and is rotating with a very high omega. So in this case, here the what is the velocity? The velocity would be omega r in this point, and in this point it would be zero because of no slip boundary condition. Correct.
Yes, correct.
And within this small distance, there is this very high velocity
Wait.
gradient created. And mind you, this delta is also very low. This delta is very, very low. The distance between the shaft and the bearing. There is a very thin film of liquid in between, and within that thin film, there is a very large velocity difference. So, due to that, here this viscous dissipation term, this becomes important. So, and
So,
cooling is a very important engineering aspect. Since it
so
heats up quite a lot, some additional interventions of cooling has to be done. So there the only source, there is a heat source due to this viscous dissipation, which comes into picture. Okay.
okay.
So moving on to last question of today's session, uh, question number 10. In an experiment, the local heat transfer over a flat plate were correlated in the form of Nusselt number as expressed in the following correlation. This correlation is given local Nusselt number at x is equal to sorry 0.035 rex to the power zero point 0.8 into Prandtl number to the power one third. Now we have to determine the ratio of average convection heat transfer coefficient over the entire plate length to the convective heat transfer coefficient at x equal to L. This question essentially asks is we have to find out the ratio of uh, the average heat transfer coefficient from x to L, from x equal to 0 to L, to the local uh, heat transfer coefficient at x equal to L. Let's try to see how we can do this. So I have this additional page over here. So I will write down the function given. Nusselt number x is equal to 0.035 rex. Let me see, rex to the power zero point 0.8 and Prandtl number to the power 1
1 by 3.
1. So this Nusselt number x, this can be written as h x by k. Here h is the local h. Let's write hx to be more precise, and this is equal to 0.035. Sorry, 0.035 rex. Okay, I'll expand out rex over here. So what I'll do is I'll write u infinity into x divided by nu to the power zero point 0.8, and Prandtl number remains as it is. So hx becomes 0.035. Front number I am bringing it in front. Front number to the power one third. There is a k which will move into the numerator, and there is a x which is coming down in the denominator. But before that, there is a u infinity by nu to the power zero point 0.8, and there is a x to the power zero point 0.8, and this x I'm bringing it down to the numerator. So this essentially becomes zero point 0.8 minus 1. So this becomes x to the power minus zero point 0.2. Correct? Okay.
Hmm. Okay, point not. Okay.
zero
Yes,
point 0.8
ma'am.
minus
No.
1. zero point
Okay.
0.8 minus
K by x you have transferred on right hand side, na?
yeah, everything. I'm just keeping hx on the left hand side because why? Because I have to ultimately reach at, my ultimate goal is to reach at average h by h equal to xyl. So I need some expression of h.
Hmm.
Okay. So h equal to x by l I can directly calculate by putting l in place of x. Okay. Instead of doing this, I will write another step. A bit messy. Hx equal to 0.035. There is a k. There is a Prandtl number to the power one third. There is a u infinity by nu to the power zero point 0.8, and ultimately x to the power minus 0.2. Okay. This is
Hmm.
the expression of hx. I will use this at least two times. Okay, my battery is low. Can you excuse me for a second?
Yes, yes.
All right. So first of all, we will calculate this average age. What is this? This is nothing but integration 0 to L uh, hx dx. So divided by L, divided by 0 to L dx. This is how we calculate average age. So 0 to L dx would become 1 by L simply, and now we will perform this integration. So here we have a lot of stuff. 0.035 k Prandtl number to the power one third u infinity by nu to the power zero point 0.8 and x to the power minus zero point 0.2. Essentially, we will integrate only this. The rest of them becomes constant. So this h bar is equal to 1 by L point. I'm forgetting this zero every time. Sorry. 0.035 k Prandtl number to the power one third u infinity by nu to the power zero point 0.8 and integration of x to the power zero point 0.2, so minus zero point 0.2. So what does that become? 1
X raised to plus 1 means zero point 0.8
again zero point 0.8. So
upon zero point 0.8.
and the limits are from 0 to L. So what we essentially get is, I'll go over here. So h bar becomes 0.035 k by L Prandtl number to the power one third. There is this u infinity by mu to the power zero point 0.8. I'm this part. So then what we have? We have x to the power zero point 0.8, and x goes from 0 to L. So this is nothing but L to the power zero point 0.8. Is that right? L to the power zero point 0.8 divided by zero point 0.8. Correct.
Yes.
So this part, this this is nothing but u infinity into L by mu to the power zero point 0.8, right? So we can write this as
R e raised to zero point 0.8.
REL raised to 0.8. So once again, this becomes 0.035 K by L, Prandtl number to the power 1/3. Okay, there is a 0.8 over here. I'm writing it in the denominator. And this becomes Reynolds number L to the power 0.8. So we got our first part, the average part, and we have to take the ratio with H x equal to L. What is that? That is nothing but um, uh, 0.035. There is K, there is Prandtl number, and in place of x, okay, so there is mu infinity by mu to the power 0.8, and this x to the power minus 0.2, I am again writing it as x to the power 0.8 by x. Is that correct? This is how we wrote it here. Okay, so this x we now have to replace with L. So I'm writing L to the power 0.8 and L over here. So this L can be brought in forward, and HL becomes 0.035 by L K, Prandtl number to the power 1/3. And once again, this part, this is REL to the power 0.8. Correct. So we got average H and we got local H at x equal to L. What was our question? Initial question was to find out this ratio, H bar over HL. So if we look at these two expressions correctly, we will see that the only factor it's differing by is the 0.8 in the numerator, 0.8 in the denominator of H bar. So this becomes 1 by 0.8, and this is nothing but, I guess, 1.25.
Yeah.
This is our final solution. So that's all for today. Any questions?
No, sir. No. Thank
So
you.
it has been a great session.
Yes.
Let's meet again next week.